Yep.
is the subject of the ProRate meeting, and
What's the name of the title again?
AMOC may be running amok.
Amok. Oh, AMOC. AMOC. Okay.
Okay,
Play on
Yeah,
words.
yeah.
that's a good play on words, and it's somewhat correct. And we're going to find out what AMOC means and why we should be concerned. And some people think that might turn us, if it gets really bad, we might get an ice age. And some people think we can't. Whatever. Let's let Paul Washington take it away. Paul's a PhD geologist. He worked at some universities in Louisiana. That's why we got to meet. And but he's not a climate scientist, but he still knows lots about geology. Go for it, Jeff Paul. And you can make it a
Temperature
little
map
bigger.
of the global temperature map. Do
Okay.
you see it now?
Yes.
Yeah. Yes.
Yeah. And you can see that the heat obviously is concentrated at the equator, that is in the tropics. Really, the tropic, the north edge of the real heat is the Tropic of Cancer, and the southern edge is the Tropic of Capricorn, with some variations which have to do with uh, surface water current flows and the like. And that is the heat. What we have today, this is basically a map from April of 24, I think it is. So it's a recent map. And you notice that the heat, the warm, the less cold water really is what we're talking about, extends far up into the North Atlantic and actually into the Arctic, up around Svalbard, uh, north of uh, north of Norway.
That's the blue
Um,
one.
that is that's that light blue zone that's headed up that way. That's
Okay.
basically a continuation of the Gulf Stream. That is not normal. Usually, the it cools off much faster and it doesn't extend that far north. That the boundary between the very cold and this current is really generally south of Iceland. But right now, it's extending farther and farther north every year. And that's because we are not the AMOC, or the Atlantic Meridional Ocean Overturn Current, AMOC, uh, is not operating fully. This is also causing the Gulf Stream along the east coast of North America to slow down some. And so you're transporting less heat northward, but you're extending it farther northward. That suggests that there is less sinking of water. Now, let's talk. What I really wanted, and this is what we mean when we say is the AMOC may be running amok. The current is not running normally, and what are the implications is the real question. So let's talk about the dynamics of the system. What is really happening here? How does this system really work? The other end of the system, just so you know, is off the coast of South and Central America, the west coast of South and Central America, in the easternmost Pacific.
Can
So
you
we've got
trace the
quite a.
Can you trace the whole path so we can have an idea of it?
Try that again.
Can you tell us the whole path of the AMOC? Just
Well,
trace it.
I will get there. I will get there. But
Okay.
let me get there from a basic principles standpoint. If we take the surface currents of the world, you can see that there are these basic gyres. They clockwise gyres in the northern hemisphere, counterclockwise gyres in the southern hemisphere. There's a tendency of water to flow westward across the tropics and eastward in the temperate zones. And so we get this gyre of effect. That's the base. On top of that, you have some other things happening. Fundamentally, those westward driven tropical currents, those westward driven tropical currents are driven by the trade winds. They were called the trade winds because they were fundamental to driving wind-driven ships across these wide open oceans, long distances, made it very much faster to follow them. The ocean, if you notice, I made a cartoon here. The top, about a kilometer of ocean is warmer, more oxygenated, number of less dense generally, but actually often a little bit saltier. But that it's where the action is going on. It's where the currents are moving. There is a fundamental thermocline boundary. They are about a kilometer down, on average, about a kilometer down, globally, which where the lower bottom water, extending to 5-6 kilometers in the deep ocean, all over the world, the deep ocean, is separated by basically they're two water masses. They're separate water masses, and so the current that we're going to be looking at is actually the one that's hidden below this. But it's driven, the whole system is driven ultimately by wind and solar aspects on the surface. So we start with the wind driving across the surface like this, and it's going to pull the water with it. And we all know that there's going to be, we think of it as a big bathtub, there's going to be a backflow in the lower water. And but ultimately, this wind is going to cause the water to get the water surface to tilt so that the water is actually piled up and reaches a higher elevation downwind than it is upwind. And that is ultimately.
What's the difference?
Try that again.
What's the difference in height?
We'll get to that, but it's in the order of centimeters.
Okay.
But those centimeters difference drive the entire system.
Wow.
Yeah, you've got such a deep, large channel to move things through that the friction is very small compared, so you don't need much driving force. So what happens is, when that happens, is that there is a tilt backwards because of the reverse flow. Now you're going to get some upward motion in the here at the on the right side of the screen, on the upwind end here, and if the wind is strong enough, you will actually get this this bottom water to break through and actually go up to the surface. And you would expect there to be downflow in the downwind end of the system. Problem is that in the Pacific, and you can see this is water levels, sea surface elevations compared to what you would expect it to be, all things being static. If you notice across the tropics, there is in the tropics, in the Pacific, there is this piling up of water against the land masses on the west side. Then there's this big plume that comes off of Japan at the going eastward. That is actually high just because of the hot, warmer water is less dense, and therefore to get the same pressure, it takes more of the water. So that's actually the elevation due to heat. You get the same thing with the Gulf Stream in the Atlantic. You get the same thing in the South Indian Ocean against by the piling up of warm water along the South African, Mozambique margin, and so the warm waters outside of that zone are mostly due to piling up to warmth, but in the tropics, it's due to actual wind-driven motion. So we get this in the Pacific, you've got that piling up of water, but you don't have a complete return flow. There is outflow of the surface water through the Malaysian, Indonesian archipelago mostly, and out into the Indian Ocean. And therefore you've got to have a bottom water inflow return. There is at the upwind end of this on the American West Coast, and I say American because it's Central and South America, West Coast, you actually have less water there, and so you have a pressure deficit. And that pressure deficit is what drives the entire AMOC system. If we go back to the current map, if you look at the North Atlantic, you are actually sinking water there. It's got to go down the bottom water to get back to the Pacific to replace the water that's coming out in the surface water currents. It sinks, it goes down the entire length of the Atlantic Ocean, comes out through the south of Africa, because it can't go the other way, the South American boundary, the Falkland Island arc, which connects the Tierra del Fuego to the Antarctic Peninsula, is shallow, so that deep water can't go through there. Some shallow water can, so you have the shallow trans-Antarctic current, but you can't get the deep water back through. So the deep water goes around South Africa, across south of Australia, and makes its way to South America, and comes up as upwelling along the South American, North Peruvian, Ecuadorian, Colombian, and Panamanian up to Costa Rica or so coast. So that's what's driving it. That differential in surface elevation between, or shall we say, in the Pacific, and we've got a different mechanism that's causing the sinking in the North Atlantic. In the North Atlantic, we don't have wind driving it as much. What we have is the hottest, saltiest water in the world is in the southern North Atlantic. Why? Because it's been at the surface all the way across the Pacific, across the Indian, around and up through the Atlantic, until it gets up to the North Atlantic, and it's been the sun's been beating on it, and it's been evaporating off the top, and so the stuff that gets to the Sargasso Sea, to the Caribbean, to the Gulf of Mexico. Well, let's face it, that's the proper term. And the reason it's the Gulf of Mexico is historical, which of course certain people don't understand, that at one time all of the Gulf Coast, except for Havana, was under Mexican jurisdiction. And when I say Mexican, I mean Spanish Mexican jurisdiction, according to the by European concepts. Of course, the local indigenous tribes didn't quite agree with them on that, but that's another issue. But it's still, that was all Mexico. So now it's now okay. So we've robbed the Mexicans of a certain amount of their heritage. Okay, so be it. Does that mean that they lost the name for the water too? Which shouldn't be. Anyway, sorry about that. Anyway, so you've got hot, salty water in the southern North Atlantic. And it is basically, because it's hot, it is less dense than it would normally be. And so it rises to a higher height, and it wants to flow off of that towards the off of that higher elevation, and it flows northward, mainly as the Gulf Stream. And in the process, it goes to less and less sunlit areas, and so it cools off. And then it runs into the Arctic, cold water coming off of Greenland. And by that point, it's cooled off, so it isn't as, it's gained density, still salty, and it becomes heavier than the underlying, denser, I should say. I call it heavy, but it's really density. It becomes denser than the underlying water column, and it sinks into it. But it can only sink into it to the extent that we're removing water from there. So this is the mechanism in the Atlantic, and this is, and the other end of the system is the upflow off the coast of South America. So if we look at salinities, you see this huge, highly saline base in the southern North Atlantic. That is what is driving everything for the Atlantic. And the other end, you see the low salinities off the coast of Panama and Colombia, and less so, but still quite, but still less saline off the coast of Peru and Ecuador. Those low salinities are because of the upflow of this huge mass of water. Yes, you're dropping more saline water in there up at the north end, but that's not the only source of water. And so by the time it makes it to the other end, it's actually less saline than the native surface water, and gives you this pattern of lower salinity off that coast. You can so what happens here that can disrupt this? Well, I'm going to go back to the sea surface elevation map. I could go, either one of these would work. But if you look at the route from that the bottom current is going to take, it basically is following just on this underneath this long raised section, the south edge of the warm water, really, of the gyres around the in the Indian and Pacific Oceans. It's going right along the edge of Antarctica at depths of 2 to 4 kilometers deep. What's happening in Antarctica right now? You're melting glaciers on the edge of Antarctica. You're putting icebergs out there, which are melting. They're all cooling off seawater, melting the seawater, and that's giving a constant flow of water into this same current belt. When you increase the amount of water coming out of Antarctica into that belt, what does it do? It lowers the pressure differential down the Atlantic because it's replacing that water. And so it makes the flow, outward flow from the Atlantic less effective. In fact, it can shut it down completely. That's probably what happened in the Younger Dryas.
Wait, when is that? What do you mean by that?
Younger Dryas was a period in the, what is it, around 9,000 years ago, 9,000 BP, when you shut down, when you cooled off the North Atlantic for something on the order of 1,400 years, and you dried out Northern Europe and interior Northern Europe, and you basically you had a massive equivalent of the Little Ice Age, a much more, a very, very major cold event. What's going to happen if we cut down, cut out the outflow or reduce the outflow is we're going to reduce the flow. We're going to reduce the ability of that cooler salt water to sink. And what's going to happen? It's going to flow farther northward. Wait, that's just what's happening right now. That's exactly what's happening right now. So if we do that, and obviously if we take it to the end ultimate where we have a major outflow, let's say we have a collapse of a couple major glacial systems, and they put a whole lot of extra water and cold water and ice into the system, so that which will melt and make more cold water, and put more water into that, we can actually virtually shut this down. Yes, it results in an initial warming of the northernmost North Atlantic, but in the end, it's going to shut down these currents so that the tropics are going to get hotter and saltier, and the northern Atlantic is going to get colder. And that's exactly what we saw in the last ice age. The last ice age, the tropical Atlantic Ocean was 5 degrees C warmer than it is today. Think about that, 5 degrees C. The North Atlantic was frozen. The edge of the ice sheets was probably somewhere south of Iceland. During the Little Ice Age, Iceland was iced in every winter. The north edge of Iceland, some winters, some summers, didn't become ice-free. In 1884, right after Krakatoa, we actually had in the winter of 1884, we had the North Atlantic off of New England froze all the way out to Nantucket. It also did that in 1815, 16 and 1816, 17 after Tambora. That's one of the reasons that I say we don't want to fiddle around with putting things into the atmosphere. It doesn't take very much to really cause a lot of problems in the northern hemisphere, the northern parts of the northern hemisphere. Pennsylvania had after Tambora, Pennsylvania had ice clogged streams in July. So that's where I'm living now, and I think it's too hot. Anyway, it doesn't. We're talking. So this is the result of a true shutdown. This is probably the fundamentals of what happened with the onset of glaciation and with some of our major cold events that have happened since the last ice age. So if we go back to our current map, yes, the gyre in the Pacific will continue. But then if we look at the historical ice boundary, it was in northeastern North America. It didn't go, yes, we had glaciers going over the ridge and into the Pacific basin, but they weren't the major glaciers. The continental glaciation was centered around Hudson Bay and reached its maximum southern extent somewhere south of the Great Lakes. In Europe, it was basically Siberia was mostly ice-free. It was European. It was the Atlantic influenced Europe, east of the Urals, that was ice covered, and that only as you go eastward in Russia, it went northward. The east, the south edge went northward very quickly, so that Moscow would have been very close to the edge of the ice sheet, not buried within it.
So I have a first cousin
The
living in
Pacific is
Germany.
going to stay warm. The Pacific basin is always going to stay warm. It's the Atlantic that goes hot or cold.
I have a cousin living in Germany. Is she gonna get covered with ice in 15 years?
The edge of the ice sheet in Germany came across somewhere around the western point of the Czech border. So is she in Munich, or is she in Berlin, or is she in
Dusseldorf.
Hamburg?
Dusseldorf.
Dusseldorf's in the middle. That'll take a while to get covered.
It's just north of Cologne in west, a little bit southwest Germany.
Yeah, but I mean, it's middle north south, middle north south. The south edge of the ice sheet was in northern France, so it comes across or somewhere around Cologne, if you wish, and then runs up progressively farther northeast as you.
And so when is this ice sheet gonna form? Under the worst case scenario?
Well, under worst case scenarios, if we have major collapses happening in the Antarctic, it'll raise the ice, the water level, and it will allow a lot more ice to push out into the ocean too, because it'll unlock some of the glaciers. You could shut it down, and it could happen. You will have the geologic record shows that at the beginning of an ice age, you have a rapid sea level rise from about where we are now, about 2 to 4 meters. That's about what we'd expect for major glacial outflow. It lasts less than 50 years, possibly as short as 20, and then the sea level starts to drop, which means that we nucleate ice sheets. Where do they nucleate? The best guess is they're going to nucleate in the highlands of the Laurentian Highlands, which are in Quebec, north of the St. Lawrence River. There's enough moisture coming off the Atlantic, off of the Gulf Stream, off of the Atlantic water, but it gets cold enough in the winter that you could potentially generate enough snowpack to over summer with the snowpack. If you can over summer in the snowpack, it will create earlier snows and multiply on itself. So what we see now is, with this warm stream going northward into the Arctic, that is a sign that we are setting ourselves up for a colder period. Is it going to be an ice age? We're already a couple degrees colder than we were. The estimates are really hard to pin down, but we are definitely a couple degrees C colder than we were 6,000 years ago, which was the interglacial maximum, and we're colder than the Romans were in the Roman warm period, which was about 250 BC to 200 AD. It was the collapse. It was the cooling off after that that caused the German tribes to come in and crush the Roman Empire in the end. Yeah, it was the ones that got pushed out by in competition for land and resources in Germany that came and invaded the Roman Empire. So, are we coming up on an ice age? Fundamentally, we should be. In the whole scheme of things, we should be. How soon will it be? To quote Yogi Berra, it's really hard to predict the future. Actually, what he said is it's really hard to predict things, especially the future. And as a geologist, I get that because we spend our lives predicting the past.
Right.
So that was my presentation.
Okay. So why is it, if this is a global phenomenon, why is it called Atlantic?
You've got the Atlantic, the AMOC is the Atlantic portion of it. They recognize the various portions first, and then they put it together. So we, being in the Atlantic basin, we tend to call it the AMOC. There's a term for the Pacific version of it. There's a term for the Indian portion of it. And I'm sorry, I can't. I have trouble enough keeping AMOC in my head, let alone trying to keep all those other words in my head. The spatial geometry, it takes all of this into account.
So I heard predictions that we're going to go up 2 meters by 2021. No, I mean
When this happens,
2100.
when the glacial collapse happens, it will go up 2 meters in less than 10 years. It's a question of when that major ice sheet collapse starts.
And then sea level will drop.
And then sea level will sit up at that higher level for long enough for the ice sheets to start to shut off the AMOC, and then for the we see cuts, we see wave cut terraces that are very shallow depth. That is, they aren't cut in that far. That suggests it's less than 50 years. But when you're going back 35,000 years ago, which is where we're talking about, dating is hard. Dating it closer than 50 years is basically impossible.
Mm-hmm.
It's a short period. It could be 20 years. It could be 50 years. It could be 70 years. I don't know. But it's going to be a relatively short period. It could be, within 10 years. I don't know how long how long does it take for the North Atlantic to cool off?
Love you, kid.
So you are pretty much opposed to the aerosol injection in the stratosphere. And you sort of said why. What would you repeat it again?
Try that again.
The sulfur injection into the atmosphere.
I started off life as a history major. I have never given that up completely. It turned, I grew up, I actually went to high school just outside New Bedford, Massachusetts. Right across a piece of North Atlantic there is Martha's Vineyard in Nantucket, just south of, just on the other side of Buzzards Bay, as they call it, there, and just south of Cape Cod, or as they call it there, Cape Cad. Yeah, I grew up with that accent. I actually had that accent for a while. I dumped it as fast as I could. Anyway, it's what, Jack Kennedy had for an accent. Anyway, that in the there were periods in the whaling record when ships got stuck in the ice out beyond Nantucket in the winters, and their captains walked to shore in New Bedford, 70 miles over the ice to get home to their to see their wives and let them know that they were going to be home, but they were stuck in the ice. And then they'd go back out to the ship. That happened in two periods. One for the eruption of Krakatoa in 1883. Krakatoa was in the Sunda Strait, right there in the middle of Indonesia. That's between Java and Sumatra. And the other one was the huge eruption of Tambora in 1815, which caused the year without a summer. The following summer, 1817, is known as the year without a summer. That we had killing frosts across the whole northern half of the U.S. and from Virginia down to Virginia and Tennessee in July. We had icing on the rivers in Pennsylvania. We had snowfall in July in Vermont. These are historical events. You know, you start playing with this system. I can relate in my own life. I was working environmental in eastern North Carolina in 1990. Was it one or two? That when what was the Pinatubo in the Philippines erupted. It was a much smaller eruption, and yet it caused a change so that I was dealing with that summer temperatures in the field in the high 80s instead of the low 90s. And that's in North Carolina. I recognize that because as a Yankee, the low 90s, and then I was stupid enough to move from there to Louisiana. But but as a Yankee from Vermont, or from New England, the low 90s were objectionable. The high 80s were uncomfortable but doable. There was a difference in my psychology for that year because of that, because of Pinatubo. I don't want to, and that was a relatively small eruption. I don't want to play with that game because the effects on growing season, climate, everything else are so dramatic, and we don't understand the system well enough to be able to engineer it. That's my position.
So even if we use it like a little bit at a time, like 1/10 of Pinatubo and see how that works, and then 1/3.
The other problem is that what it will do is it will cut down on evaporation, which will cut down on precipitation especially in the marginal areas. It'll cut down on precipitation everywhere. But in a place like Louisiana, where you're getting 60 or 70 inches of rainfall a year, if you cut back to, 55 to 65 inches a year, that isn't going to change your water budget dramatically. But if you and here in the Northeast where I am, where we're getting 30 to 35 inches, 30 to 40 inches a year, it might cut it back to, by 10%. But if you're in Kazakhstan, growing wheat in Kazakhstan, or growing or in Uzbekistan, on the edges of actually that isn't the Gobi, that's anyway, that the Karakan desert there. Uh, you are this could take you from having 14 inches a year to having 10 inches a year. And that changes you from being high plains level of precipitation to desert level of precipitation, and change it whether you can actually grow anything at all. If you're on the south edge of the Sahara, in the Sahel, you're in that same position. You lower the precipitation at all, and you have famine. And those are the places that will be hurt the most by doing this.
Well, we're in a drought in New Orleans. We normally have 60 inches a year, and my grapefruit usually have 100 or so baby grapefruit at this time, and 80% of them fell off already. I don't know what is bad, but as much as you say is bad, we already experienced that. And I see the only hope for getting back to a normal climate is cool off the poles.
Well, yeah, thawing out the poles is not really doable. Well, I mean,
I said cooling the
oh,
poles.
cooling the poles.
Yeah.
Well, what do you say to the people in
Norway.
Edmonton? Edmonton is well north of the latitude of Oslo or Helsinki. So it's grain grown.
Right now, the people in Norway right now are worried that there's going to be 1 billion climate refugees, and a major percentage might go to them, and they don't want it. They don't want those people there.
Well, you've got to realize that if you raise the sea level, if you were to raise sea level 4 meters, you will displace 10% of the global population.
I believe that.
There are 8.5 billion people on Earth. You will have 850 million approximately refugees. You will have most of Bangladesh having to evacuate into India. There's a reason that they're separate countries. They fought a war over that back in 1950.
The bottom line, though, is this seems to be where we're going, and what you're talking about doesn't sound worse.
Well, we're going to go through that, and then we're going to have the growth of the ice sheets. That's the problem. We're not going to, and given the amount of heat that is already stored in the oceans, it seems unlikely that we're going to stop the melting of the Antarctic margin.
I had a question. Are you familiar with maybe the cold blob or warming holes in the Atlantic? So I'll just give an example. There's a really good New York Times article. I don't know if my subscription's up to date, so I'm just going to use this one from Science Line, since I think you used Science Live for the original discussion. But the idea of a cold blob or a heat sink, I guess they're putting forward maybe the idea that AMOC delivers much of its heat, but it might be a little more stable than we first think, and maybe the subsurface temperatures are more controlled by, let's say, ocean current. But either way, it was just someone from the National Oceanography Center who was saying that there's a lot of different factors that play into this, and measuring overall heat versus the subsurface heat versus the closer to the surface heat might not give the full picture.
The problem that I've seen with all of with most of the people who are working on the AMOC, they tend to focus on the downflow in the Atlantic as the fundamental forcing factor here.
Yeah.
And what I am saying is that when you analyze the flow pattern in the system, the fundamental forcing factor is the meltwater off of the edge of Antarctica. Because and that the everything in the Atlantic is a response to that. Yes, you have more warmth. It's causing more melting on of the of in more meltwater to come off, cold meltwater to come off of Greenland. You've got, and that would be a stable system if it weren't being interrupted by this greater amount of meltwater coming off of the edge of Antarctica. The meltwater coming off of Antarctica is interrupting the outflow from the AMOC, which is necessary to keep the AMOC running.
Okay, Tor wants to say.
I know Tor has the hand raised.
Tor, you want to say something?
Yeah, that the meltwater theory doesn't line up with the evidence that I have. For one, the Younger Dryas is now strongly linked to the end of the Clovis and a bolide impact on the ice sheet, which would push an immense amount of rose up.
Except that there is no geologic evidence of that bolide. That is an atmosphere. No, a bolide hits a bolide that would do anything of that level on the ice sheet would leave a geologic imprint underneath it.
Again, if it's a comet, it's going to blast the ice. What they do know is
a comet is also going to leave it's going to leave an impact signature in the sub ice. The ice was never more than a couple of kilometers thick. These things, even a comet hitting at something like 40 kilometers per second or 35 kilometers per second is going to make an impact signature that extends a good 10 kilometers deep. And that means it's going to leave a mark that would be seen. This is something that the impact people which I have worked in that space, are very familiar with. In fact, the impact people generally just say, no, if you don't see the impact signature, it either has to have disappeared tectonically or it didn't happen.
Or it came in at a very low angle, or it
no,
broke
by the time it hits, mechanically, an impact is going to be at a high enough angle that it will make a mark, and it will be roughly circular. It does not, there is not a glancing blow thanks to our atmosphere and our gravitational field.
Yes, there was an impact strike in Amazon, I think 1920s. I don't have the exact date, but it came at such a low angle that it skipped. It did not leave a significant impact crater.
That wasn't an impact. That wasn't a meteorite strike. That's crap science, because that was actually give me a second. I'm missing the word right now, but it was an eruption of a type related to kimberlites that produced not a diamond bearing one, but it's one of those types of eruptions. The only one in the historical record.
Okay, well, the evidence in the Clovis villages shows charring, microdiamonds, and platinum group metals. That is a bolide.
Well, platinum group metals. The platinum group metals were I demonstrated to the Berkeley group back in 1981 that the platinum group metals were all that they were using as evidence of impact were all terrestrial. That was that. There's a signature there that of the ratioing of the platinum group metals is that of the in the KT boundary clays is that of the hot spot that is sitting down what 2,000 miles south of India. It was the source of the Deccan trap, and that is coincident. That is at the time of the impact, and that the ratioing is not that of any known extraterrestrial source.
Well, how do you explain the microdiamonds?
Microdiamonds are known all over the world. They are a high grade metamorphic product from that you find, and we find diamonds all over the place. Where you've had glacial scouring of high metamorphic materials.
And you know the difference between the two?
There isn't any difference between the two, except that you don't get diamonds. You don't get diamonds from an impact. You get certain type. No, you do not. Diamonds do not form in impacts.
No, they don't. They form,
and they don't get. They form at 200 kilometers deep in the earth and are brought up by volcanic action.
Yes, but those have different isotopes. They have different inclusions. The ones that
but the ones in the metamorphics are formed in very, very deep subduction zone systems, such as what's going on underneath the Himalayas right now, that are then brought up by isostatic rebound later on. This has been well established in the structural geology and tectonics literature, which is my primary field.
Let me just ask a question. Okay, for those who are sitting on the sidelines, assuming you guys resolve this, what's the consequence of asserting that it could be a meteor or not in terms of predicting the future?
Meteors aren't going to. Meteors are interrupters in the system. Meteors are not a steady state system. We have a steady state system that goes through periodic crashes in temperature or periodic temperature changes that are producing episodes of continental glaciation interspersed with periods of continental warmth. This is the standard icehouse Earth of the 220 million year cycle that hit its warm period in the mid Cretaceous, late dinosaur period, and had its previous cold spell in the Triassic, started in the Pennsylvania. In other words, about 250 million years ago, 250 million years ago, more or less 220 million years ago was probably the peak of it. It's about the same period, strangely enough, as the galactic year for the solar system, the galactic orbital period.
Okay, so going back to the aerosol injection in the stratosphere comment, it's hard for me to believe that the bad stuff that's happening on the planet, we do nothing, is not worth getting rid of, and how the things that you don't know you might get could be as bad as what you know you will get.
Well, let's put it a different way. You're looking at it from a very privileged economic situation. And when I say that, I'm not talking about you personally, but from a society that's in a very privileged position where very few very little of the food production is being produced in marginal environments. And where we can't have the resources to acquire replacement food when we have a failure of one or another pieces of our food production system. If you were living in the sub-Saharan Sahel, the south edge of the Sahara, or you were living in the Atlas or other Mediterranean margins of northernmost Africa, you are living in an area where they have to either produce food from marginal environments or marginal systems, or they have to be given food because they do not have the economic base to acquire food readily in competition with groups like us. Europe and North America are very privileged. The rest of the world is not as much so. And what we're looking at, what would happen here is we as the privileged would be subjecting the less privileged to a life of to a situation of hardship, food hardship. We are doing so with Iran right now. We are setting it up for Iran right now. We don't need to do it with by screwing up the atmosphere too.
Wait. You're saying that Iran's food processing is
no,
less...
the closing of the Strait of Hormuz is cutting off the supply of fertilizer to much of the world right. at planting time, which is and cutting off the supply of fuel at planting time. This is setting us up for a really bad harvest this next fall.
So what about what's going on in Israel? They live in a relatively arid part of the Mediterranean.
But they are also a very economically privileged society.
Reporting in progress.
Okay, but they had to learn how to do desalination and, turn forests into green areas. So they did a lot to mitigate the problems of their climate.
They have also cut off most of the water to Amman, Jordan, and the West Bank Palestinian areas. Amman, Jordan has had rationed water for 40 years now.
Mm-hmm.
Because the Israelis are taking 80% of the water from the Jordan Basin.
Mm-hmm. So this is not a place where the solutions are coming.
No, but Israel is, as I say, economically privileged for the Middle East. It is able to acquire things that other places in the Middle East, other countries in the Middle East can't afford. Especially the marginal populations in those countries.
Okay. Well, that's an important thing to understand. Well, anyway, I don't know how much time. We're after 9 o'clock, so
Yeah, I'll stop the recording and we can wrap up.
okay.